We've spent like the last decade treating artificial intelligence like this oracle on top of a mountain.
Yeah, that's exactly what it is.
Right. Like, think about how we actually interact with these systems today. If you, as the user, want answers, you basically have to hike up the mountain, you type out a prompt, hit send, and your device beams that request way up into the cloud. It pings around these massive, power-hungry server farms.
We're talking clusters of GPUs that cost hundreds of millions of dollars to build.
Exactly. And they require the electricity of a small town just to keep the cooling systems running.
Right.
Then, assuming your signal is even good, the answer floats back down to your screen. And we've completely accepted that as the absolute unbreakable rule of how high-level reasoning just has to work.
It really is. I mean, it's the core structural constraint that we built the entire tech industry around over the last several years. The underlying assumption has always been that, well, true intelligence is inherently heavy. To get complex reasoning, you need massive parameters, right? And massive parameters require massive infrastructure.
But what if the mountain was completely unnecessary? What if we've been building all this infrastructure for a problem we just hadn't, engineered our way out of yet?
That is the big question.
And that brings us to our mission for this deep dive. We are looking at a foundational document that, frankly, shatters that whole cloud computing assumption.
It really does.
We are unpacking a massive announcement from March 31st, 2026, released by a new AI lab called PrismML.
And we really need to emphasize the stakes here, because this isn't just like an incremental software update or a slight bump in processing speed.
Right.
PrismML has announced the release of 1-bit Bonsai, which is the very first commercially viable 1-bit large language model.
Wow.
Yeah. We were talking about fundamentally freeing artificial intelligence from the cloud entirely.
Okay, let's unpack this, because to truly understand why an offline 1-bit model is such a tectonic shift, we kind of have to look at the exact trap the AI industry has been stuck in.
Yeah, the bigger is better trap.
Exactly. The rule of the last decade was simple. To make models smarter, you just made them bigger. You feed them more data, give them more parameters, and require more memory and costs to run them.
Which, from a pure capability standpoint, it worked.
Right, it did.
That brute force approach gave us the whole AI revolution. It gave us models capable of writing complex code, drafting legal briefs, reasoning through multi-step logic. But it created this severe deployment paradox.
A paradox.
Yeah, because the most capable intelligence became entirely trapped in these massive data centers.
Which creates a bizarre bottleneck for you, the listener, trying to actually use this stuff. We have this hyper-capable intelligence, but it's completely disconnected from where the actual work happens in your life.
Exactly.
Like, think about where AI is actually needed the most. It's on your phone when you're in a dead zone trying to pull up information. Or it's split-second real-time decisions without waiting for, network latency to ping a server in Virginia.
Oh, absolutely. Or inside highly secure enterprise environments.
Like hospitals.
Yeah, hospitals or law firms, where strict privacy laws mean the data legally cannot leave the physical building. You can't just send confidential patient records to a cloud oracle.
No, definitely not.
And that is the exact problem PrismML is claiming they've solved with 1-bit Bonsai. They've severed that tether to the cloud. But doing so requires a completely different approach to the architecture itself.
Right. And honestly, when I first read the documentation, this is where my own skepticism really flared up.
Oh, I'm sure.
Because historically, when I hear the phrase model compression or, low-bit models, I immediately think of the visual equivalent.
Which is?
Trying to email a massive, beautiful photograph, and you compress it so much to fit the attachment limit that it just turns into this blocky, pixelated JPEG.
Ah, right. The artifacting.
Yeah. You get a much smaller file, sure, but you lose all the critical detail. In AI, doesn't shrinking a model usually mean completely lobotomizing it?
Basically, yes.
You get a small memory footprint, but the AI starts hallucinating, or it forgets how to follow complex instructions.
And what's fascinating here is that PrismML completely agrees with your skepticism on that.
Oh, really?
Yeah, they actually explicitly state in the source document that low-bit models have traditionally been incredibly painful compromises.
Okay.
When you compress an AI that much, they lose their multi-step reasoning capabilities. They fail at reliable tool use. They essentially just fall short of being deployable for any serious production-level product.
So how do they prove they aren't just another pixelated JPEG?
Well, to prove that Bonsai is entirely different, PrismML doesn't just point to standard run-of-the-mill benchmark averages. They introduce a completely new core metric to the industry, which they call intelligence density.
Intelligence density, I mean, it's a great term, but how exactly are they calculating the density of intelligence?
It's a very specific mathematical formula. Instead of just looking at raw benchmark averages, which, can be easily skewed,
Right.
PrismML calculates the negative log of the model's average error rate across rigorous tests, and then divides that number by the model's physical size in gigabytes.
Okay, hold on. The negative log of the error rate.
Yeah.
Why the complex math? Why not just say, hey, Bonsai scored an 85 out of 100 on the test?
Because linear metrics fail entirely when you are pushing the absolute boundaries of physics and engineering.
How so?
Let me put it this way. Pushing an AI's accuracy from 60% to 65% is relatively straightforward. You just feed it a bit more training data.
Okay, that makes sense.
But pushing an already highly capable model from 95% accuracy to 99% accuracy, you are fighting severe diminishing returns.
Oh, I see.
It requires an exponential leap in architectural efficiency to squeeze out those last few percentage points of error near the absolute ceiling.
Right. Getting from good to great is hard, but getting from great to perfect is nearly impossible.
Exactly. A simple average treats all percentage points equally. But the negative log formula heavily weights those improvements at the very top end of accuracy.
Okay.
It's measuring the actual refined mastery
Yeah.
packed into the physical bytes of the model.
That makes a lot of sense, actually. You are rewarding the model for achieving the hardest possible gains, not just the easy ones.
Exactly.
So when we apply this new metric, how does one-bit Bonsai actually score?
The numbers are frankly staggering. The one-bit Bonsai 8B model, meaning it has roughly 8 billion parameters, achieves an intelligence density score of 1.06 per gigabyte.
Okay. And compared to others?
Well, for context, if you look at its absolute closest peer in the industry by parameter count, the Qwen 3 8B model, it scores just 0.10 per gigabyte.
Wait a second. 1.06 versus 0.10.
Yes.
That is a 10x leap. That's a 1,000% increase in density.
Yeah, it's not a marginal step forward. As the researchers point out, Bonsai is operating in an entirely different regime of computing.
Okay, but claiming a 10x leap in density is one thing. Actually engineering it is another.
So, absolutely.
How do you physically pack that much intelligence into a space that small? To figure that out, we have to peek under the hood at the bit level, because the sources make it clear they didn't just optimize existing technology.
No, they didn't.
They fundamentally re-architected it from the ground up.
And this is the part of the paper that gets me so incredibly excited, because from a pure engineering standpoint, it's a masterpiece.
Let's hear it.
The one-bit Bonsai 8B is a true one-bit model, end-to-end. And I cannot overstate how rare and difficult that is to achieve.
Why is it so rare?
In the past, researchers trying to build low-bit models would rely on what PrismML calls higher precision escape hatches.
Escape hatches, so they would, cheat the compression.
Precisely. They would compress the bulk of the model down to 1 or 2 bits, but they knew that if they compressed the most sensitive parts, the model would collapse into gibberish.
Right.
So they would leave the really crucial components in standard 16-bit or 8-bit precision. But PrismML didn't use a single escape hatch. They forced every piece of the architecture down to 1 bit.
Let's actually define those pieces for a second, because the text lists them out, and it really highlights the scale of this achievement.
Go ahead.
They are talking about the embeddings, which is the translator that turns human vocabulary into numbers the machine can read. The attention layers, right? The AI's short-term memory that connects the beginning of your long document to the end.
Yep.
The MLP layers, the multi-layer perceptrons, which are the actual reasoning and logic centers of the network. And the LM head, the final piece that selects the exact next word to output.
Exactly. Normally, if you compress the logic centers or the attention layers down to a single bit, which is literally just a 1 or a 0, the simple binary switch, the AI loses all of its nuance.
It just forgets how to reason entirely.
Right. But PrismML figured out how to make embeddings, attention layers, MLP layers, and the LM head entirely 1 bit across all 8.2 billion parameters without losing the reasoning capability.
Which brings us to the physical reality of what that means for you, the user. Because it is entirely one bit end-to-end, this entire 8 billion parameter class model fits into a microscopic memory footprint of just 1.15 gigabytes.
1.15 gigabytes.
That is wild. We're talking about an 8B class model. Usually a standard 16-bit 8B model is massive, requiring 16 gigabytes of RAM just to open it, let alone actually run it.
Oh, easily.
Bonsai is roughly 14 times smaller than its full precision peers. 1.15 gigabytes is smaller than a cached Spotify playlist.
Which completely inverts the hardware requirements we discussed at the start.
Right.
You no longer need a data center. You don't need a $4,000 desktop computer.
Right, and here's where it gets really interesting, because that transitions us perfectly into what happens when you actually put this microscopic model on consumer hardware.
The demos are fantastic.
Yeah. The sources provide several real-world demos, and this is where the theoretical engineering translates into massive productivity gains. Let's use an analogy here. Think of a traditional 16-bit model, like a really smart employee, but every time you ask them a question, they have to take a 10-minute commute to a massive filing cabinet down the hall to get the information.
I love this analogy.
Right. Your computer's processor is incredibly fast, but it's physically starving for data because the 16-bit memory footprint is just too massive to move quickly. The commute takes too long.
Exactly.
But 1-bit Bonsai shrinks the entire filing cabinet down so small that the employee is just sitting right at your desk with all the files already in their hands. Suddenly, the data flows instantly.
That lack of memory friction changes the entire user experience, and you see it clearly in their first demo. They show the model running the Math 500 benchmark.
Okay.
Now, as a baseline, a standard 16-bit 8B model physically cannot fit on an iPhone. The phone doesn't have the unified memory to hold it. It is literally impossible.
Right.
But 1-bit Bonsai 8B, it fits effortlessly on an iPhone 17 Pro, and it runs at approximately 40 tokens per second.
40 tokens per second running natively on a phone. Just to visualize that for everyone, a token is roughly equivalent to a word. 40 words a second is significantly faster than any human being can read.
Oh, way faster.
It's generating answers faster than you can skim them, and it's doing it in airplane mode.
And to show how unprecedented that is, they compared it to a standard 16-bit model that is small enough to fit on a phone, a tiny 1B parameter model.
Okay, so a much smaller model.
Right. And that much smaller, far less capable 1B model only ran at 23 tokens per second. So Bonsai is not only vastly more accurate because it has the reasoning power of 8 billion parameters, it's nearly twice as fast as a model a fraction of its size.
But 40 tokens a second on a phone is just the floor. If you take that exact same 1.15 gigabyte memory footprint and give it more compute power, the bottleneck completely vanishes.
Oh, it flies.
On an M4 Pro Mac, it hits 131 tokens per second. And on an RTX 4090 desktop GPU, it hits a blazing 368 tokens per second.
It's incredible. But, reading speed, the raw throughput, that is really only half the story here.
What's the other half?
The third demo they highlight is perhaps the most important indicator for the actual future of AI deployment. They simulated a long-horizon agentic task.
Okay, let's define an agentic task real quick. This isn't just asking the AI to write a haiku or answer a trivia question. This means giving the AI a complex job that requires multiple sequential steps, sustained reasoning, and memory retention over a period of time.
Exactly. So specifically, they simulated summarizing and assigning IT support tickets.
Okay, so real office work.
Yeah. This means the AI has to read a messy log of a user complaining about a broken system, diagnose the actual problem, categorize the severity, and then write a clean summary for a human technician to address.
That's a lot of steps.
It is. They ran this locally on an M4 Pro Mac, putting the 1-bit Bonsai 8B up against the standard 16-bit 8B model in the exact same time window.
The ultimate showdown.
Exactly. The standard 16-bit model managed to complete 6 tickets in a given time frame.
6 tickets.
1-bit Bonsai 8B completed 50.
Wait, really? 50 versus 6 in the exact same time window.
Yep.
That implies the 16-bit model isn't just slower at outputting the text of the summary. It's physically choking on the memory requirements of the task.
That's exactly it.
It's struggling just to hold the context of the messy IT log in its memory while generating the answer.
Right. Because of the dramatically higher throughput and the near-zero memory overhead, the 1-bit agent is capable of doing exponentially more actual work. It's thinking and moving simultaneously without hitting a wall.
That is a staggering productivity difference,
Oh?
but it immediately brings up a very practical anxiety for anyone listening.
The battery life.
Yes. Blazing speed and doing 50 tasks at once is amazing, but if you've ever tried to run a heavy application like rendering a video or playing a high-end game on your laptop, you know exactly what happens next.
Fans spin up.
The fans spin up like a jet engine, the laptop turns into a space heater, and your battery is dead in 20 minutes.
Yep.
Running AI locally usually drains power incredibly fast. So how does Bonsai solve the energy crisis of local AI?
This is a crucial point because energy efficiency isn't just a convenience issue for your battery life. It dictates the fundamental economics of AI.
How so?
If it costs too much power to run a model, it can never become invisible, foundational infrastructure. The documentation shows that Bonsai delivers roughly 4 to 5 times better energy efficiency than its 16-bit counterparts.
The specific numbers from the text are remarkable. On the M4 Pro, it requires just 0.074 milliwatt hours per token. And on the iPhone 17 Pro Max, running natively, it's even lower, 0.068 milliwatt hours per token. You could generate thousands of words of complex reasoning without even watching your battery percentage drop.
Exactly.
But wait, I have to push back on the hardware physics here for a second.
Okay, go for it.
Current consumer hardware, like the M4 chips in Apple devices or the NVIDIA RTX 4090 you just mentioned.
Yeah.
Those physical silicon chips were built and optimized for full precision 16-bit math. They are wired for heavy calculations. They aren't designed to natively run 1-bit operations. Yep. So how are we seeing massive efficiency gains on hardware that wasn't even built to exploit this architecture?
If we connect this to the bigger picture, that is the most exciting implication hidden in this entire document.
Yeah.
You're completely right.
Okay.
The massive speed-ups and the 4 to 5 times energy gains we are seeing right now on Macs and iPhones are coming almost entirely from the reduced memory footprint.
So it's just the commute getting shorter.
It's simply the benefit of moving less data from the RAM to the processor. The employee already has the files at their desk. But the future of this tech is mind-blowing.
Break that down for us. What happens when the hardware actually catches up to the software?
It comes down to the fundamental physics of silicon. Because the model's weights are truly 1 bit, meaning every parameter is just a 1 or a -1.
Right.
It allows the linear layers, the reasoning engines in the network, to perform inference by skipping complex multiplication entirely.
Skipping multiplication? Wait, how does it calculate anything?
Well, in traditional 16-bit AI, the silicon chips are constantly multiplying massive, complex floating point numbers together, billions of times a second.
Sounds exhausting for a chip.
It is. Multiplying complex fractions requires a huge amount of logic gates in the silicon, which takes computation time, draws heavy voltage, and generates heat.
Okay.
But with 1-bit weights, you aren't multiplying fractions anymore. You can replace all that heavy multiplication with simple addition and subtraction. You just flip signs and add.
And addition is fundamentally cheaper to process.
Dramatically cheaper. It requires far fewer logic gates, which means less power drawn, which means almost zero heat generated.
Wow.
Right now, our chips are still using their heavy multiplication circuits to do the simple math. But once we get dedicated 1-bit hardware, chips designed specifically to just do addition at massive scale, the documentation suggests performance and efficiency could jump by another whole order of magnitude.
Another 10x leap on top of the 10x leap we already have. That is genuinely hard to wrap your head around. We're talking about AI that uses less power than a screen backlight.
Exactly.
And we've spent this entire deep dive establishing that the 8B model is a paradigm shift. But to PrismML's immense credit, they didn't just release one massive flagship model, and they didn't lock it away behind some corporate API paywall either.
No, they didn't. They understand that to change the industry, you have to flood the zone. Alongside the 8B, they released 2 smaller sister models.
Okay.
The 1-bit Bonsai 4B and the hyper-compact 1.7B.
And the text notes that together, these 3 models violently shift what's known as the Pareto frontier.
Right.
For those who might not use that economics term daily, the Pareto frontier is essentially the absolute optimal trade-off curve between 2 competing factors. In this case, the intelligence of the model versus its physical size.
Yeah, that's a good way to put it.
Think of it like buying a car. You can buy a cheap car or you can buy a fast car. The Pareto frontier is the absolute fastest car you can get for the absolute lowest price.
Right. And for this announcement, they charted 20 of the leading Instruct models in the world, ranging from 1.2 gigabytes to 16.4 gigabytes.
Okay.
Previously, the frontier, the absolute best reasoning performance you could physically get at any given size constraint, was defined by models like Qwen 3 and Mistral 3.3b.
Right.
The Bonsai family dramatically moves that entire curve to the left. If someone suddenly builds a 200-mile-per-hour supercar that only costs $5,000, they have shifted the frontier.
Yeah, it is insane.
That's what Bonsai represents. It's an entirely new boundary of what is physically possible in computing.
And the absolute best part of this announcement is that this isn't just theoretical research locked in some ivory tower lab. They are democratizing this new frontier today.
Yes, they are.
The model weights for all 3 sizes are available right now under a highly permissive Apache 2.0 license. Anyone listening to this can go find them on Hugging Face and GitHub.
Yep.
They run natively right now on Apple devices via the MLX framework, and on NVIDIA GPUs using llama.cpp.cuda. You can literally download them and run them today.
It really speaks to the broader philosophy of the team behind this. PrismML emerged from a group of Caltech researchers, backed by some serious industry heavyweights.
Like who?
Khosla Ventures, Cerberus, and Google. And in their documentation, they explicitly note that they are consciously mirroring the historical arc of all human innovation.
Yeah, that historical comparison in the text really stuck with me. Like, think about early computing.
Oh, yeah.
The first computers used to fill entire rooms and required a huge team of specialists to operate. Early cameras used to require elaborate, deliberate setups with explosive flash powder and long exposure time.
Right, it's a whole ordeal.
First, humanity proves something is mathematically or physically possible. But the real revolution happens when we figure out how to make that exact same technology smaller, cheaper, and accessible to everyone.
Exactly.
Today, supercomputers and high-def 4K cameras live entirely in our pockets, completely integrated into our lives. PrismML is essentially arguing that the exact same transition, the shrinking of the room-sized mainframe, is happening right now with advanced AI. Which perfectly wraps up the mission of our deep dive today. We've officially gone from massive cloud-locked intelligence that demands hundreds of millions of dollars of infrastructure and latency-heavy internet connections to production-ready, one-bit AI that lives offline, securely, and hyper-efficiently on the exact devices sitting right in front of you.
And, if we step back and look at the broader implications here, this raises an incredibly important question.
What's that?
One that isn't explicitly written in the PrismML text, but hangs over every single data point and demo we've discussed today. If incredibly capable, fast, and secure AI can soon run entirely offline on our personal devices without ever needing an internet connection, how might that fundamentally change our relationship with data privacy and the tech giants?
Oh, wow. Yeah, that completely flips the current dynamic.
Think about it. Right now, your data is the product. Every prompt you write is logged.
Right, on a server somewhere.
But if you have a one-bit AI running locally, will we stop thinking of AI as a service that we constantly connect to and feed our personal data into?
That makes sense.
Will we start thinking of it as an inherent private capability of the physical objects we own, like a calculator or a flashlight?
I like that.
When you turn on a flashlight, it doesn't phone home to Apple or Google to ask for permission to shine. It just works.
Right.
If high-level reasoning becomes completely invisible to the $100 billion data economy, that fundamentally reshapes the future of the internet.
That is a fascinating and honestly slightly disruptive thought to leave on. The oracle isn't on top of the mountain anymore. The oracle is just sitting right in your pocket, and it doesn't report to anyone but you.
Precisely.
Thank you so much for joining us on this deep dive. Keep questioning the consensus, keep exploring, and we'll see you next time.